Hello everyone, welcome to Biotechnology. My name is Farah Marfi. In the last video, we have already discussed the theoretical principle behind sedimentation and centrifugation. Today we will discuss the physics behind sedimentation, and we will also see how the sedimentation, acceleration, velocity, or you can say the centrifugal acceleration and the centrifugal force are correlated with each other. But before we move forward, be sure to click the subscription button and turn on the notification bell so that you won't miss any future videos. Now let's get into it. Suppose this is a biological particle having some mass and acceleration, and a force F is applied onto it, then the particle will move into a particular direction. According to Newton's second law of motion, then force will be equal to the mass into acceleration. M here represents the mass and A here represents the acceleration. So in this situation, we can have a mass in terms of density. Then density represented by rho will be equal to the mass upon volume. And then if we carry this mass to this side, then mass will be equal to rho into V. And we put the value of the mass into this equation. We will get a final equation of F is equal to rho VA, like this. Let's suppose we have a test tube filled with some medium and we immerse this biological particle into it. Then the particle must be having some density and will be represented as rho P, and the medium also having its own density represented as rho M. Rho P here will be equal to density of the particle, and the rho M will be equal to the density of the medium. Let's suppose this is a center of access for any centrifuge, and the tube containing the particle is held like this into by its holder. So when a rotatory speed is applied to it, then the particle will follow a circular motion. The particle will experience here the particle will experience two type of forces, and one force will be the centripetal force that exists towards, or you can say that resides towards the center of axis, and this is the centripetal force. And the another force is also applicable to the particle at the same time, or you can say the particle experiences the another force, and that force is called the centrifugal force. And the particle here feels like to throw away out of the test tube. In this condition, this particle will sediment here at the bottom of the tube. The CF here represents the centrifugal field, and we consider this is equal to the F1, and the CP here represents the centripetal force. Actually, that centrifugal force is a pseudo force. This force actually, or you can say naturally, does not exist, but only experienced by the particle, and the value of the force experienced by any particle is rho VA. So here in this situation, we consider this F1 as F, or you can say the centrifugal force. All are same. F1, F and the centrifugal force all are same and will be equal to the rho VA. The density here is the apparent density because there are two type of density resides here. One is rho P and one is rho M. So this is an apparent density. So according to this, when we put or we consider both the density, then the formula will be equal to the rho P minus rho M bracket close and V into A. V here represents the volume of the particle and A is the acceleration. Since the particle is spherical, so the value of the V will be, or the uh, formula for the V will be 4 by 3 pi r cube. And A is here a centrifugal acceleration because it's acting in a centrifugal field. So we can write the A as C also, or you can say we represents the A as C here. Then the formula will become rho P minus rho M bracket close 4 by 3 pi r cube into C. Let's consider another condition that also existing here, that when a particle is experiencing a centrifugal downward external force, then at the same time the medium here having a some density puts a counter force onto it, and this phenomenon is well explained by the Stokes law. And this is the counter force, and that force we here consider as F2, and that F2 will be equal to 6 pi eta RV. The eta here represents the viscosity of medium, and R here represents the radius of particle from the center of axis. So this F1 and F2 here will act on this particle at the same time while we are moving this particle into a circular motion. And the particle sediments only until and unless the F1 and F2 gets equal. Means initially the F1 and F2 is not equal, but as soon as they get equal, the particle sediments out. So let's understand this by an example. Suppose we have a box and we are applying a force onto it. So suppose we are applying a F1 force onto it, then the box will move into the direction of the applying force F1, and from the another side someone else is applying a force, that force is F2, a counter force, and the tendency of the force is comparatively less than the tendency of the F1 force. So the box will move into the direction of the F1 and keeps on moving to its direction. But as soon as the F1 and F2 gets equal, then the force counter each other and the box will not move into any direction and will come to rest condition. Similarly, the particle here also, when reaches at the bottom of the tube, then the F1 and F2 will be equal to the 0, and the particle will sediment out. Considering this situation, when F1 gets equal to F2, and from the previous equation, when we put the value of the F1 and F2 here, we will get the equation like this: rho P minus rho M 4 by 3 pi r cube into C equal to 6 pi eta RV. V here represents the velocity of the particle. Now we want to solve for the velocity, or we want an equation for the velocity of the particle. So when we cancel this 4 with 6, we will get 2 here and 3 here, and we cancel out this pi with pi, r with another r, we will get 2 more r here, and then equation will become rho P minus rho M upon eta into 2 by 9 r square into C. And when we simplify it more, then 2 by 9 r square rho p minus rho m upon eta into c. This is the sedimentation velocity. This is the velocity with which the particle gets settled down at the bottom of the tube. This is the sedimentation velocity. And let's bring this c downward here, opposite to this equal sign. Then the equation will become 2 by 9 r square rho p minus rho m upon eta. This v by c means the sedimentation velocity upon the c here is the centrifugal acceleration. So the sedimentation velocity upon the centrifugal acceleration will be the sedimentation coefficient and is represented by the symbol S. This is also called the Swedberg unit, and you must have seen this Swedberg unit S somewhere when you were studying about the ribosomal subunits. Example as 30S and 60S. Now let's talk about the centrifugal acceleration, that is C. The value of the centrifugal acceleration is equal to omega square r, and r here represents the distance of the particle from the axis of rotation. It is not the radius of the particle, but it is a distance from the axis of the rotation. And omega here represents the angular velocity, and angular velocity is equal to 2 pi s. Let's understand this more clearly. Since you know that c is equal to omega square r, and you also know that omega is equal to 2 pi s. S here represents the rotor speed, and the value for the unit for the c is centimeter per second square. The rotor speed is in the terms of revolution per minute, and now you want it in terms of the revolution per second. So for that you have to divide 2 pi s with 60. Then the equation will become 2 pi s divided by 60. Then the whole term will be represented as revolution in terms of what? Revolution per second. And when you will put the value of the omega into this equation, then c will become the 2 pi s divided by 60 whole square into r. And when you make it more simplified way, then the value will be 2 pi square s square 360 divided by 3600 into r. So this was the equation for the centrifugal acceleration, and in several books this centrifugal acceleration c is also represented with g, or with g, and this is actually a applied centrifugal field, or sometimes also called as applied centrifugal force. Let's suppose you have divided this g with a gravitational constant small g, then the whole equation will become RCF. RCF is what? RCF is relative centrifugal fold or relative centrifugal field. So this was all about the RCF and sedimentation coefficient, angular velocity, applied centrifugal field. And these equations are very important in solving the several numericals that are being asked in several exams from time to time. And you can also refer to a book named Principle of Biochemistry by Wilson and Walker. So thank you for this video. Hope you have liked it. Thank you so much.